Welcome to Lecture 8. I think in the beginning of the course I told you that there were two very important lectures I was going to give, and the first one was right off the bat with the equivalent loads. You're about to be tested on the equivalent loads and your understanding of that concept in week 5 on your first exam. Within that, equivalent loads were great. They were not statically correct. They're not real loads, they're equivalent loads. They allowed us to take the tendon out, replace it with loads, and get the same answer. Of course, those loads were offset by, the loads on the concrete were offset by the loads on the tendon, so statically nothing was happening. And you remember a fundamental concept of that was that, and again, you will be tested on that in week 5, is that in a statically determinate beam, pre-stressing cannot, will not, is incapable of creating reactions. So, and when we looked at those equivalent loads, when we put those equivalent loads on a statically determinate member, we got a moment diagram. If we just looked at the concrete only, we separated out the tendon, we looked at the concrete only, looked only at the equivalent loads on the concrete, that created a moment diagram that was equal to the force times the eccentricity between the center of gravity of the concrete and the center of gravity of the tendons at every location. So we would get the primary pre-stressed moment diagram in a statically determinate member by placing the equivalent loads on the member. That's what was so powerful and useful. But no reactions were created by doing that. You may remember earlier in the course, I showed you that we'll take that statically determinate beam with that profile. That would want to have a deflection up. While there are no reactions, statically nothing is happening. There are stresses and there are deflections. So hopefully at this point, as you're about to be tested on that stuff is clear. And it'll all come out in the wash on the test if it's clear or not. But then if you recall, to make a point, I added an interior support. So that interior support had to create a downward reaction on that beam, an actual external reaction that completely offset the deflection that would happen if that support wasn't there. We discussed that creates a true reaction. So, in statically indeterminate members, there are reactions created by pre-stressing, just simply due to the pre-stressing. There are no loads. I've got no loads. We're back to that weightless, loadless beam. Secondary effects, it's very important that you understand this, are caused entirely by pre-stressing, and they have nothing to do with the external loads. But they create reactions. Those reactions will create real shears, and those real shears will create real moments, and those are all called secondary effects, secondary reactions, secondary shears, and secondary moments. And they are absolutely critical. I said two very important things in the beginning of the course you will see that apply to pre-stressed concrete and largely to post-tension concrete that you'll never see in any other material. You took wood, maybe, hopefully, steel, your regular concrete design. You didn't talk about any of these things, and you never will in any other material. This is only, exclusively for pre-stressed concrete and primarily post-tension concrete. This stuff doesn't happen in pre-tensioned concrete. They can't make indeterminate members. These things are fabricated, stressed in the shop. They're put on a truck. They're carried. They're placed by a crane. They can't have secondary effects. This is a beam or slab system that's locked into its supports, and then it gets stressed. Then it tries to deflect, and it can't. So we're really only talking about post-tension concrete when we're talking about secondary effects. Always indeterminate. So that secondary reaction down, holding that beam down, creates a secondary moment diagram. One thing to note is that secondary moment diagram is always linear. It has to be. There are no loads in between the supports. There's nothing happening, nothing's going on over here. These real reactions are just reactions to supports. Everything in the secondary effect category is only happening at the supports. It's the restraint of the supports. The beam or slab wants to deflect and it can't because of this. Now, rumors and wives' tales has it that nobody had ever considered this before, and somebody at some time in history built a test situation in a lab at a university that had a couple spans. They stressed the beam, and apparently the beam ripped itself right out of the interior support. And it occurred to them there must be some reactions happening. So I don't know if any of that's true, but it makes for good stories. So, secondary moment diagram, always linear between supports. Every once in a while, I get some of you students, especially you Cal Poly ones, who have been out and you've been working somewhere and using PT Data or ADAPT or one of the other programs. And those people who use those sometimes refer to these as hyperstatic effects. You'll never hear me use that term. I don't know who came up with that. Well, I actually do, but I'm not going to tell you. But that's not a code term. There is no ACI code term called hyperstatic events. The code refers to these as secondary effects, and that's how we will refer to them. And anything else is slang and something that someone thought was cute to make up. So you won't be hearing me say hyperstatic effects, and I hope you don't either. It's not the correct terminology. It's something that someone came along who sells software who decided they didn't like using the code notation and definitions and created a new, stranger sounding, this stuff sounds like it's more complicated, hyperstatic. I don't even know what that means. I tell you here, I think hyper means that my kids are spazzing and bouncing off the walls. And how you can be hyper and static at the same time, I don't know. Because it seems like you can either be hyper or you can be sitting static. But I don't know how you're both at the same time. Anyway, secondary effects. So here is the process again. We have a beam. For right now, that is weightless and loadless. Okay, we're just talking about pre-stressing. And I will likely test you on just whether or not you understand that as a concept. Now I told you, and I kind of lied to you, I said we were done with equivalent loads and the stress concept. We're done with the stress concept. We are in the strength, failure, everybody running out of the business. Everybody running out of the building phase of the design. We're just saving lives here. But we're going to go back to that equivalent load concept only because it makes our life easier. It actually makes it very easy to calculate what these secondary effects are. And I will show you how that is done. Remember, we take the equivalent loads, put them on the beam. When that was statically determinate, we got the primary pre-stress moment diagram out of it. At every location, it would be ordained that the moment on the concrete only would be the force times the eccentricity. That's not the case when we put these equivalent loads on a statically indeterminate beam. We're going to get a moment diagram, but it's not going to be F times E at all locations. It's not going to be F times E at any location, actually. In your homework number 4, I'm going to have you draw and superimpose these two moment diagrams. The primary pre-stress moment diagram, F times E, and the final equivalent moment diagram. And what you're going to see, let's see if I can get this. Hey, let's pretend that this met up, because I drew that so pretty. So if those started at 0, everything would be great. The difference between these two diagrams, it's building from 0 here, if I drew that correctly, to the largest point here, is actually this diagram. It's actually linear. The difference between these two diagrams is a linear diagram, building to a maximum here, starting at 0 here. So as I said, the moment diagram, the secondary moment diagram, will always be linear between the 2 points. But I'm going to have you draw these two diagrams superimposed on each other and hopefully prove that to yourself. So if this was statically determinate, this would be the moment diagram we get. Because it's not, we put the equivalent loads on and we get this moment diagram. The difference has to be the secondary moment diagram, has to be the secondary effects. That's why this equivalent load method is so powerful. I can just go straight to the final equivalent load moment diagram, final pre-stressing moment diagram, subtract out the primary from the final, and get the secondary. When I have the secondary moment diagram, I can calculate the secondary shears in each span. And that shear will be that reaction in this case. The sum of those two shears will be that reaction. And this will be that reaction. So if you're thinking in terms of load case, this is what the code is actually telling us we have to do. We must, according to the code, include the secondary moments. In fact, that part is right here. Required strength shall include internal load effects due to reactions induced by pre-stressing with a load factor of 1.0. So if you think in terms of what the loading is on the beam, we actually put the factored load, 1.2 dead plus 1.6 live, distributed load, we'll talk about distributed loads right now, plus this set of secondary reactions. Notice one thing about the secondary reactions, they must sum to 0. Pre-stressing didn't create additional weight. So, statics says that these reactions must sum to 0. Statics, your best friend. Statics is a good best friend. Never going to tell you that, you look fat in a pair of jeans, or it's never going to hit on your boyfriend or girlfriend when you're not around. Statics is, you could do a lot worse as far as best friends. So a code requirement that we include these secondary reactions. And I don't know if I'm beating a dead horse or not, but in a statically determinate member, the things you're going to be tested on up through your first exam couldn't create reactions statically determinate members. Statically indeterminate members, so more than 2 supports, keep it simple, those will create secondary reactions. Those are real reactions. They're not invented like equivalent loads aren't really loads. These are real reactions. They must be included. Therefore, while the code didn't feel the need to put this into an equation form, which is a little frustrating, what it meant is that, what that means is we had to come up with our own term. Post-tensioners had to come up with their own term. It's not in ACI. ACI just has this statement. So if you want to put it in an equation form, we've created, and in this course, we will call this M demand. Be careful, please. I want you to go out sounding intelligent about post-tension concrete. MU is not the demand moment. MU, by definition, is 1.2 M dead plus 1.6 M live. That's an ACI definition, not a Dirk Bondy definition. This section says we must include load effects due to reactions induced by pre-stressing with a load factor of 1.0. In other words, the secondary moment. So our terminology, and I want you to have this correct, when you are including secondary moments, that you are creating the demand moment. That is the moment we must provide capacity for in post-tension concrete. And a lot of people just throw around MU and M demand is the same thing. I don't want to see you doing that. I want it very clear. I want to see that you understand MU has a specific definition, and that'll even become more important when we get to the shear portion, because shear is as confusing as it possibly can be. But you understand, even though you won't find it in the code, that all post-tensioners call this the demand moment. The factored moment plus the secondary moment. Okay, let's look at an example. This came from example 1 in chapter 4. The 4 inches, the 7 inches, 186.2 kips of force. The equivalent load only, and be careful about this, when I'm having you calculate the secondary effects on your homework assignments, and that's all I'm asking you for, you've got to go back and only do the pre-stressing loads, not the net loads. Net loads have nothing to do with anything from this point forward. So one of the things I see students just starting to calculate net loads, and it tells me that you're really not following what I'm saying. You're not buying what I'm selling. What I'm selling right now is you only look at the pre-stressing equivalent loads. Remember, we had the distribution factor set up. We worked on this. But I think we did the net loads in that case. We are just looking at the pre-stressing equivalent loads. I do a moment distribution, and the final, this is the final. Whenever we put the pre-stressing loads on the member and calculate the moments, that is the final pre-stressing moment diagram. Now, when it's indeterminate, that's made up of a primary and a secondary. But we end up going straight to the end, calculating the final. Then we use the fact that we understand what the primary pre-stress moment diagram is to extract out the secondary. So, we've kind of learned that the only place in a two-span beam that the action is happening secondary is at this location. What we're trying to do is figure out what the secondary moment is here, because it will go to 0 here and it will go to 0 here. And it's happening due to the reaction down here. There will be a reaction up and a reaction up, and those won't affect the secondary moment. This one does. So remember, at support B, we had an eccentricity of 4 inches. Let's not get confused on that. The eccentricity was this number. Between the CGC okay, so F times E at that location is the primary pre-stress moment diagram, or the primary pre-stress moment. So at that interior support, 62.1 foot kips is the primary pre-stress moment here. Remember, that's going to look so we're taking the difference between that primary pre-stress moment and the final pre-stress moment. So that's the primary, F times E. Secondary is going to be the difference between those two, or 227 foot kips. So the secondary moment diagram, 227 is the moment in between the primary and the final pre-stressing moment diagram. So we can extract out what the reactions are. If I know what the moment diagram is here, remember the secondary moment is causing tension at the bottom of the beam. So the moment must be going this direction, creating tension at the bottom. So there will be a shear here and a shear here. Same thing on this side. That same 227 is creating reaction here and a reaction here. So on the left side, 504 going up, going down, 5.68 going down, going up. From the shear diagram, from knowing the shears, I can always get the reactions. This must satisfy statics, so that's one thing to check. And the sum of the moments about any point will also satisfy statics. Okay, well, we got out the secondary moment. Let's put on the factored loads. 1.2 dead, 1.6 live. Find the fixed end moments, do the moment distribution. Calculate MU, not M demand, but MU. And we'll find the shears due to MU. Remember, my personal favorite, you don't have to do this, but, you know, take it from a guy who's been doing this. I'm 57 years old as of this taping. Probably be 58 when I'm talking to you. But I like to take WL over 2. Look at that, look at that. Then I take the moment, get the downward force and the upward force. Those have to be equal. This is what I like about it, is these numbers are equal. These numbers are equal. It's just that these are going in different directions. So the moment reaction subtracts from the WL2 over reaction over 2, and it adds over here. Or the shear. I should say shear, not reaction. Shear. Do the same thing on this side. 52.8 from WL over 2. Take that 603 moment, get an up and down force of 15.1. They subtract on one side. They add on the interior support. And I get a shear diagram. I get a real reaction. That's from the factored loading. We're talking real reactions now, real shears. I know that the slope of this line is 2.64 kips per foot. So I take that divided by 2.64 kips per foot to figure out where the moment crosses 0. I use that information to know that the change in moment is equal to the change in moment between these 2 points. That gets me this positive moment. Remember, once we have the negative moments, every span is statically determinate, so we can get everything else out of it. And again, in the same process, I get this moment. One more time. The area under the shear diagram is the change in moment between 2 points. So it's the change in moment starting at 603 minus the area under this. So be careful. Every once in a while I get a student that just calculates this area and says it's the positive moment. That's not true. In this case, calculating this area would be the positive moment because you started at 0. So this is what the code is telling us. We must provide capacity. We've already calculated and figured out how to figure out what the capacity of pre-stressed concrete members are. Now we're checking against demand. So while the capacity was very familiar to you, we added one more tension force, and that was the pre-stressing. So that all looked very familiar to what you have done already in your reinforced concrete class. It's actually the demand that is the curveball thrown to you in post-tension concrete. Demand moment is MU, so this is our MU diagram. At every location plus M2. Now notice a few things. First of all, MU is 603, but the second 603 with tension on the top of the beam. We're above this line, so tension is on the top of the beam. Draw all my moment diagrams to the tension side. This is also drawn to the tension side. Secondary effects cause tension, unless you've done something very weird, on the bottom of the beam in the interior, or between the two ends. Pretty much every time you're going to get tension on the bottom, unless you've got some very strange pre-stressing profile. So notice that when I superimpose this 603 minus 227, I actually only have to design for 376 foot kips. That may seem very strange to you, but that is the statics. That is the truth. I get a lot of people, when they come to that realization, they say, oh my gosh, well, shouldn't you just design for the 603 foot kips? No. That's not statically what is happening. At failure, the secondary moment diagram is always there. It's always the same thing. It's always the same thing at service stresses, at factored loads, at plastic. At any time you want to look at this diagram hasn't changed. Now this diagram goes from being much smaller at service loading to factored loading, of course. But this one never changes. So we're designing for a substantially smaller negative moment. But notice that the positive moments, we started at 400 foot kips here. If this were all lined up, which it should be, we actually are adding moment to the positive moment. The secondary effects add to the positive moment. So in that case, we are required to design for 487.8 foot kips of positive moment here. But I want you to think about something. Many academics, when this first was discovered, I'll say, their first choice was, and code writers, was to try to eliminate secondary effects. The very early sections of the code said ignore them, but that's like saying ignore statics. Say that 2 plus 2 is 5. That's just incorrect. So quickly that got rectified. So secondary effects then became an absolute requirement of the code when smarter people came along and looked at that. My father being mainly the guy I'm talking about. So the academic world decided, well, then we must figure out how to eliminate these secondary effects. They're scary. They're going to scare children. This is terrible. We must get rid of them. Well, I will show you what the academics came up with to try to do this in a minute, and I may test you on that, but it's of absolutely no practical use to any of us. But let's talk about something here. Okay, so we'll take a T-beam. And really, we're always talking about T-beams. So realistically, this is only going to happen in a cast-in-place floor. We're only going to have indeterminate members when we pour the concrete in forms and make multiple spans. So we're always really talking, if we're talking about a beam system, we're talking about T-beams. So what that means is that we'll have negative moments, and for negative moments, the steel is up on the top. That's how that's going to get resisted. And for positive moments, we're going to put steel down here, and that's how that will get resisted. But let's think about something here. Remember, we just went through this. Remember when we had positive bending, we had this little tiny area, Whitney stress block, up at the top, and our centroid of compression was way the heck up at the top. So we had, between the compression face and the centroid of concrete compression, I'm sorry, shouldn't have said any of that. Between the tension steel the TC couple between these two, T and C, was the greatest. That was the greatest arm. That's going to give us the best capacity. In other words, in positive bending, where tension is at the bottom of the beam, it's a very efficient section, and we kind of went over that already. So if you were going to, if secondary effects were going to increase some of the moments, you'd want those moments to be the positive moments, because that's where it's very efficient to resist them. So if we're going to bump up some moments from MU, in the spans would be where you wanted to do it. If I look back at this isn't going to work. So now we'll look at negative moments. Where we have negative moments, we have tension steel on the top and a compressive block down at the bottom somewhere of a much skinnier compression face. So in this case, our centroid this arm has gotten smaller than it was for positive bending. So it's a little less efficient, or kind of a lot less efficient, to resist negative moments with the T section than it was to resist positive moments. So this is exactly what we'd want. If you could decrease the negative moments while increasing the positive moments, and this is the section you're working with, which is always the section we're working with, that's a benefit. I mean, that's a redistribution of moment away from an inefficient location to a much more efficient location. So there's no reason. What I'm getting at is the hype and panic that the academic world felt because they had to include secondary effects, and then the attempt to try to remove them has never made any sense. Secondary effects help. They make a design more efficient. There is nothing to run away from. Okay. This is a source of confusion sometimes, so I hope you just sit back and listen. The code makes that statement that we talked about. This section is with respect to flexure. So what they're saying is that in the flexural design of these beams, you must include the secondary effects. There is no such statement about the shear design. Now, let's be really clear. We're in the academic world. There are secondary shears. There are secondary reactions. They exist. You can be tested on those, and for this class, they always exist. The code is silent on whether or not you need to include the secondary shears in the shear design of beams. So the world, software programmers, people who write books, have not included the secondary shears in shear demand. I want to make this real clear again because I had a problem on a test because I made that statement and people thought they could just ignore secondary shears on the test. Secondary shears are here to stay. They're very important. They exist, and if I ask you a question about them, the last thing you want to do is tell me we just ignore those and don't do the calculation. That will not bode well for you on the exams. They are real. What I am telling you is that there is no such... The world evolved such that there is no demand shear. We will just design for VU when it comes to the shear design of the course. So I'm just telling you that. I didn't make the rules. I just have to follow them just like you. But they're real, and I can test you on them, and I probably will test you on them. So secondary reactions, secondary shears, and secondary moments are something that are very important to me. Code is interpreted, or people have interpreted the code as saying you only need to apply secondary moments in your design. So that's the way the world went. Not correct, not statically correct, but it's what happens. What I will say in defense of that is the secondary shears are relatively small. Not insignificant, not ignoring, but they're pretty small. So if you didn't do it, it's probably not the end of the world. So when the academic world decided that they wanted to figure out how to get rid of secondary effects, they love to teach pre-stressed concrete and parts of it that nobody needs, uses, or makes any sense. And that may be one of the reasons the pre-stressed concrete courses in general throughout the country and throughout the world are not taught anymore. Because they just taught weird things. But here's one of the weird things, and I may test you on this. This is something, it's not practical. We don't do it in practice, but it's a mental game. So it will show if you really understand pre-stressed concrete. So I may test you on that. So this was the pre-stressed concrete only final diagram that we got by just putting the equivalent loads on. I didn't have the positive moments before, but I've added those. So pre-stressed only, equivalent loads only, 2-span indeterminate beam, we put those loads on. We got this moment diagram. Now I ask you, how could I get the same exact effect without creating secondary effects? Well, and you're about to be tested on in week 5, that if there were no secondary effects, the moment at every location would be the force times the eccentricity. In other words, the final pre-stress moment diagram would also have to be the primary pre-stressing moment diagram, which would mean that every one of these locations, every location, the force in the tendons multiplied by the eccentricity between the center of gravity of the concrete and the tendons would be equal to these numbers. So if that were the case, there would be no secondary moment diagram. The primary pre-stress moment diagram and the final moment diagram would be the same. Subtract the two, subtract the primary from the final, you'd get 0. So there wouldn't be secondary effects. So that's how the academic world proposed eliminating what they found to be scary, secondary effects. So how would we go about doing that? How would I test you on that? So if we take this 289 foot kips and we divide by the force, that would have to be the eccentricity that we would need between the center of gravity of the concrete and the center of gravity of the tendons. If we had that eccentricity, then that force times the eccentricity would equal 289. So let's see what happens. I take the 289 foot kips, divide by the 186.2 kips that I had put in the tendons, and we need 18.6 inches of eccentricity, such that the primary and the final moment diagrams would be the same. However, we don't have 18.6 inches to work with. Remember, between the center of gravity and the concrete and the top of the beam, we only had 8 inches. So, we'd be 10 inches. We'd have to put the post-tensioning up here somewhere. That's not going to happen. So what's the other way to do this? Well, at the midspan of the beam, if you buy this, okay, this isn't going well. This is where I was going. This is actually the closest that the tendons in this example ever get to the face of the concrete. So this is the tightest dimension we have to work with. It actually matches that dimension. So, if I take this moment and I actually divide it by that 4-inch eccentricity, by the way, which isn't the 4 inches from the top, it's the eccentricity between the CGC and the tendon. Remember, that CGC was 4 inches from the top. It's also 4 inches from, coincidentally, between the center of gravity. Yeah. Do better. So the eccentricity is 4 inches. Not to be confused with the dimension from the top of the beam, which also happens to be 4 inches. So if I take that moment, divide by the maximum eccentricity that I can have, what do I get? Well, I get a new force. So to stay within the beam and keep the tendons from, having to be built a foot up in the air above the beam, I actually need to change this force. And so that was determined based on this condition. Now if I take the positive moments and divide by that new force that I have, I get the eccentricity required there. And based on the eccentricity that would then be required here, and I'll let you work on this so you can think about it, that creates 19.7 inches from the bottom. So this profile would give us this force and this profile. Give us exactly the same final pre-stress moment diagram. The difference is it would also give us 0 secondary effects. So when I calculate the balance loads here, put them on primary pre-stress moment diagram, and the final pre-stress moment diagram would be the same thing. This profile eliminates secondary effects. So spend a little time as you're preparing for exam number 2, not exam number 1, but in the 8th week. This is fair game to ask you about. Ask you for a profile that does not create any secondary reaction, shears, or moments. What I'm asking you is to provide a concordant profile. And this is how it's done. Now, why would we never, ever, ever do this in reality? Well, we took 186 point something. Yeah, 186.2. Now we have to provide 875.8 kips of force. So dramatically, almost 4 times the amount of pre-stressing is now necessary. We hardly drape the thing. All for the so-called benefit of eliminating secondary effects. So it costs a tremendous amount more. We are barely draping and taking advantage of the post-tensioning. But this is what the academic world tried to push for a while and didn't catch on, doesn't make any sense. Nobody who knows, who's actually studied this is afraid of secondary effects. They're not complicated. It's not scary. There are still people today that want to talk about the complications of secondary effects and how baffling it is, and that students like you could never understand this. That is just wrong. Just hasn't been presented correctly. So that concept, extremely important. And let me summarize. The capacity of a post-tension or pre-stressed concrete beam is very similar to what you came to this class already knowing how to do. You have one more force in there. That's the force in the pre-stressing steel. And the only complication in finding that is determining what the FPS value is. And you're going to make sure you use the correct equation. The unbonded equation from this point out. Unbonded for beams. So that part's not at all difficult. This isn't particularly difficult either, but the real trick, and where my focus will be on your second exam and what I'm testing you on and what I want you to really leave this class understanding, is that the demand changes in post-tension concrete. In indeterminate members, which we always have, you're probably never going to, in your entire 40-something year career, design a statically determinate post-tension member. They're always poured in place, cast in place, multiple spans, and indeterminate. So it will be the demand that changes, and that is very confusing to people who've never really understood what we're talking about. I've seen people try to match hand calculations with computer output, and they don't understand that the secondary moment needs to be included. They will calculate MU only and think that their program's giving them terrible answers on the amount of reinforcement that's required. That's just a lack of understanding, but it's not complicated. You'll be tested on it. Most students who study this will do just fine. And it's a very interesting, unique part of post-tension concrete. Okay, that is the end of Lecture 8. We're about to go on to Lecture 9, which is shear, which all I can do is apologize for. It's not my fault. It's a messy part of this, but we're gonna get through it together. See you at lecture number 9.